Attention deficit/hyperactivity disorder, or ADHD, affects roughly 5 to 10% of children and approximately 4% of adults worldwide, making it one of the most common neurodevelopmental conditions. Yet it is also one of the most misunderstood. The name itself is misleading. People with ADHD are not unable to pay attention. They can hyperfocus intensely on tasks they find engaging or novel. The problem is that attention is not reliably under voluntary control. ADHD is not caused by poor parenting, lack of discipline, or a character flaw. It is a neurobiological condition rooted in differences in brain development and neurochemistry, specifically in the circuitry that governs executive function, reward processing, and attention regulation. Understanding the neuroscience reveals why the condition manifests the way it does and why the treatments that work are the ones that do. The central neurochemical story in ADHD involves two neurotransmitters, dopamine and norepinephrine. Both play critical roles in the prefrontal cortex, the region of the brain responsible for executive function, which encompasses working memory, impulse inhibition, task switching, planning, and the ability to sustain goal-directed behavior over time. In the ADHD brain, the synaptic signaling of dopamine and norepinephrine in the prefrontal cortex is dysregulated. Research suggests the baseline level of dopamine signaling in key circuits is lower than in neurotypical individuals. The prefrontal cortex depends on precisely calibrated dopamine and norepinephrine concentrations to function optimally. Both too little and too much impair executive function. The ADHD brain tends toward the lower end, leaving prefrontal circuits working below capacity. Reward processing is particularly affected in ADHD. The brain's reward system, centered on the nucleus accumbens and the ventral tegmental area in a circuit called the mesolimbic dopamine pathway, evaluates the expected reward value of activities and generates the motivation to pursue them. In the typical ADHD brain, this system has a higher threshold for releasing dopamine in response to low-stimulation activities, the routine, repetitive, or delayed reward tasks that make up much of daily life. Put simply, the dopamine release that a neurotypical person experiences from completing a homework assignment or a work task is blunted in the ADHD brain. The nervous system seeks higher stimulation activities to achieve the same dopamine signal. This is why novelty, urgency, competition, or passionate interest can produce near-normal focus in someone with ADHD. These contexts generate enough dopamine signal to engage the executive system. Neuroimaging studies have produced a striking finding. The brains of children with ADHD show a consistent pattern of delayed cortical maturation. Specifically, the thinning and thickening of the cortex that marks brain development follows the same sequence as in neurotypical children, but on a timeline approximately 3 years behind. The prefrontal cortex is the region with the greatest delay. This is not damage, it is deferred development. Many of the executive function difficulties in ADHD can be understood as a mismatch between the developmental stage of the prefrontal cortex and the demands being placed on it. This finding also explains the partial improvement many people with ADHD experience in late adolescence and early adulthood, as cortical maturation eventually catches up, though in the majority of cases, some degree of executive function difference persists into adulthood. ADHD is classified into 3 presentations: predominantly inattentive, predominantly hyperactive impulsive, and combined. The hyperactive impulsive presentation, the stereotypical fidgety, interruptive child, is the most visible, but the inattentive presentation, which involves primarily difficulty with focus, organization, and mental follow-through without prominent physical hyperactivity, is common and frequently underrecognized, particularly in girls. Executive function deficits affect not only attention but also working memory, the ability to hold information in mind and manipulate it in real time, and inhibitory control, the ability to suppress prepotent responses. Emotional dysregulation is also common and increasingly recognized as a core feature. The same prefrontal circuits that regulate attention also regulate emotional reactivity, and many people with ADHD experience intense emotions and difficulty de-escalating them. Stimulant medications, methylphenidate, amphetamine compounds, are the most studied and broadly effective treatment for ADHD. They work by increasing the availability of dopamine and norepinephrine in the synaptic cleft. Methylphenidate primarily blocks the reuptake transporter that removes dopamine and norepinephrine from the synapse, while amphetamine both blocks reuptake and promotes release of dopamine from presynaptic terminals. By raising synaptic dopamine and norepinephrine concentrations toward the optimal range, stimulants improve the signal-to-noise ratio in prefrontal circuits, enhancing executive function. Non-stimulant options including atomoxetine, a selective norepinephrine reuptake inhibitor, and guanfacine work through related mechanisms. The effectiveness of these specific mechanisms provides strong indirect evidence that ADHD is fundamentally a neurochemical condition, one where the neurobiology, not the behavior alone, is the appropriate target of treatment.